Welcome friends to my YouTube channel Somo Physics. Now in my previous lecture I have discussed about few heat capacity relations. Okay, so in today's lecture I shall going to discuss few other relations related to that heat capacity. Okay, so our today's first issue is that we have to find out the ratio of adiabatic to isobaric volume expansivity. At first today we will calculate the ratio of adiabatic to isobaric volume expansivity. We all know what is alpha s. We all know 1 by v del t s constant, increasing volume per unit rise in temperature. And since there is a s, we put a s. And what is alpha p? That is similarly 1 by v del t pressure constant. Okay, so this cancels. So what we get? So if we take it in denominator, so this becomes del t del v s, and this is del t pressure constant. Okay, so this is what is this? We can write PSTV. So my del T del Vs means minus del P del S volume constant. Del P del S volume constant, and this is del V del T pressure constant. Okay, this we can write this. Now this can be written as del P del T volume constant into del T del S volume constant into del V del T pressure constant. Okay, fine. So we take this term to numerator. So this becomes del S del T volume constant by, this is simply del P del T volume constant into del V del T pressure constant. So we multiply both by T. So what we get? This is simply CV, and we all know that this means Cp minus Cv. We derived it previously. Okay, so if we eliminate this minus sign, it would become Cv by Cv minus Cp. So if you divide both sides by Cv, what you get? If you divide this both sides by Cv, you get 1 by 1 minus gamma. Okay, so this is the ratio of adiabatic to isobaric volume expansivity, that can be written as 1 by 1 minus gamma. Okay, this relation we derived it previously, that Cp minus Cv equals to T into del P del T volume constant del V del T pressure constant, that we can write 1 by 1 minus gamma. Okay, so this is our first lecture. Okay, now next, our second issue is that by using Maxwell's relation, first now I am going to show that heating produced in adiabatic compression. Okay, so heating, we all know that in adiabatic compression heating is produced. So heating is produced in adiabatic compression. Okay, adiabatic compression. So how we can show it, or how we can justify it by using Maxwell's relation? So we use this relation, that is del T del P S constant. This we can write del V del S pressure constant. Okay, we use this relation. Now we can write this term in this way: T1 by T del V del S pressure constant. Okay, so what is this? T del S means del Q, so this we can write del Q. Okay, this we can write T1 by T del V del S, so T into del V del Q pressure constant. Okay, so this we can write T into del V del T pressure constant into del T del Q pressure constant. Okay, we write this T del S as del Q, so T into del V by del Q pressure constant, and del V del Q means del V del T del T del Q. Okay, now as I told earlier that alpha is the coefficient of volume expansion, that is increase in volume per unit rise in temperature. So from which we can easily write del V del T pressure constant, this equals to V alpha. So here we can write V alpha. And what is this? We all know Cp means del Q del T pressure constant. So this is 1 by Cp. Okay, so we have write this expression del T del P S constant means Tv alpha by Cp. Now for a change in pressure dP, what would be the corresponding change in temperature? Okay, for a change in pressure dP, if the pressure change is dP, then what will be the corresponding change in temperature? We can write dt. So dt can be written as Tv alpha by Cp into dP. Now just see this equation. Here all the quantities are positive. Temperature is positive, V is positive, alpha is positive because 1 by V del T. This is positive. So Tv alpha, Cp all are positive quantities. This means dP is positive. So clearly we can say that heating is produced during adiabatic expansion because all the quantities in right hand side are positive. So dt is positive, that means heating is produced in adiabatic compression. Okay, so this is simple. Now let us move to third problem, that is cooling is produced in adiabatic expansion. Okay, now we will do the reverse case. Cooling is produced in adiabatic compression, and how we can prove it? Cooling is produced in adiabatic compression. Okay, cooling is produced in adiabatic compression. Okay, so cooling is produced in adiabatic expansion. How we can check it? So in this case we use this relation, that is del T del V S, this equals to minus del P del S volume constant. Okay, we can write it minus del P del S volume constant. Now just write it in this way, that is del P del S volume constant, and we can write this as del P T del S means del Q. Okay, so minus T into, we can write del P del T volume constant del T del Q volume constant. Okay, del P del T volume constant, del T del Q volume constant. And what is this del P del T volume constant? This is pressure coefficient, that is 1 by P del P del T volume constant, that is pressure coefficient, that is increase in pressure per unit rise in temperature keeping volume constant. So this is pressure coefficient, or you can say beta P, increase in pressure per unit rise in temperature. So from which this is positive. So del P del T volume constant we always beta P. So what is this? Minus T into beta into P, and this is what? This is 1 by CV. Okay, so this is 1 by CV that we can write. Okay, now a closed loop to this equation. Okay, at first, now if the change in volume is dV, then what will be the corresponding change in temperature dt? We can write minus T beta P by CV into dV from this relation. Okay, now if you see this equation, T is positive, P is positive, CV is positive, beta is also positive, because beta we write 1 by P del T volume constant. So at constant volume P increases with T. So beta is positive and temperature, pressure, CV all are positive. Okay, but due to the negative sign, the temperature decreases or the temperature is negative. Okay, so okay, all the terms are positive, but since there is a minus sign, temperature decreases. So we can say cooling is produced during adiabatic expansion. Okay, so fine. Now let us move to another problem. Okay, our problem number 4 for today, for isentropic transformation. Okay, for isentropic process, we have to find out, show that this del V del Ts, this equals to minus Cv by Cp minus Cv del V del T pressure constant. Okay, del V del T pressure constant. So for isentropic process, del V del Ts, this is equals to minus Cv by Cp minus Cv into this. Okay, we have to show it. So we have to start this from first TDS equation. From first TDS equation, that is Cv dt plus T into del P del T volume constant dV, from first TDS equation. Okay. Now for isentropic process, entropy remains constant. That means this term is 0. So what we can write? We can write Cv dt, this equals to minus T del P del T volume constant dV. So from which we can write Cv, this equals to minus T del P del T volume constant del V del T S constant. Okay, so del V del T S constant, Cv, this equals to minus T into del P del T volume constant del V del T S constant. So for isentropic process, change in entropy is 0. So from left hand side we put 0 and Cv we can write this. Okay, now we start this from RHS. We can prove this from RHS because it will be more easier to do it from RHS. So what is given in RHS? Minus Cv, okay, by Cp minus Cv into del V del T pressure constant. Okay, now just what is Cv? Cv we put this, so minus plus T del P del T volume constant del V del T S, and here we put del V del T P. Now what will be Cp? Cp minus this will be Cp minus Cv, and we all know that Cp minus Cv is, if there is a famous relation, T into del P del Tv into del V del T P. So this cancels, this cancels, T cancels. So what would remain? Del V del T S constant. So it is given in LHS. So left hand side is equal to right hand side. Okay, so this is very simple. We must have to remember that we have to start it from first T and ds equation. How I can know that by just saying this minus sign, because if there is a plus before, we will start second TDS equation. Okay, so this is the simple case. Okay, so let us do another similar problem like this. Okay, so let us do another similar problem again. Question number 5 of today. For isentropic process, we have to show it del P del Ts. This equals to Cp by Cp minus Cv del P del T volume constant. This is also similar. Now since there is a plus sign, so we have to use the second TDS equation, that is TDS. This is equals to Cp dt. There is a minus, so by putting 0, when it be, you will rearrange in such a way that Cp will be positive. So T del V del T pressure constant into dP. Okay, so for isentropic process this 0. So what we can write? We can write Cp dt. This equals to T del V del T pressure constant dP. So what will be Cp? T del V del T pressure constant del P del T is constant. So this will be my Cp. Now here we also start from RHS. Okay, here we also start from RHS. Okay, so what will be my Cp? This is RHS. Cp by Cp minus Cv del P del T volume constant. So what is Cp? This T into del V del T pressure constant del P del T S constant into del P del T volume constant. Now I can erase it because I have already substituted the value. Now what will be Cp minus Cv? T into del P del T volume constant del V del T pressure constant. Okay, T cancels, del P del T volume constant cancels, del V del T pressure constant cancels. So what will we remain? Del P del T S. Thus you see in left hand side, this is equal to left hand side. So this is also is easy problem. So whenever you are asked to do anything by using isentropic process, you always always use T and ds equations, because T and ds there, and in isentropic process ds is 0. Okay, so remember, for isentropic process you always use T and ds equations. Okay, so let us move to the last numerical of today's lecture. Okay, last numerical of today's lecture. Okay, here given P, this equals to f of v into t. Okay, we have to show that s increases with v. S increases with v. How we can show it? Okay, now P, this is given function of v into t. So what will be del P del T volume constant? If you do it with respect to t by keeping volume constant, so this will be f of v. Okay, so what will be f of v? That is P by T. Okay, now what we can write from Maxwell's relation? PTV means SVT. So del S del V T, this equals to P by T. So this is positive. So what we see? Entropy increases with volume. Simple. Given that P equals to f of Vt, so what will be del P del T volume constant? This is f of V. And what is f of V? P by T. Okay, simple. And what is del P del T volume constant? Del S del V temperature constant. This is equal to P by T. And since it is positive, so entropy increases with volume. Okay, so S increases with Dear guys, this is all for today. Now in my next lecture, I shall going to discuss about the latent heat equations. Okay. So if you don't subscribe my channel, then kindly subscribe it to get latest videos on physics. Okay. Thank you.